Sorry? No. Well, the recording started. Hello, I'm David. I'm the coordinator of the Maths Learning Centre. Everyone in here, you've met me already, but people who are watching online, this is what I look like, in case you ever want to know. And that's enough. Just so that when people come to the Maths Learning Centre and say, hey, this guy said on the revision seminar this thing, so yeah, that was me. It's happened a lot, so I try and put my face on it every so often. And are there more lights? I really tried all week to make more lights, but no, can't make it happen. I'm sorry. Okay. So it's semester 1, 2019. It's Intro Math Econ Basic, and which I hate that name. It's not like it's basic. Like it's not like it's easy. It's just the first one. So they really should just say Intro Math Econ 1A or something, just to say it's the first one. I've been given some requests of things to talk about. There were quite a few things about partial derivatives, so I might start there. Okay, so the point of derivatives is to track how something changes when something else changes. And so we have in our head that there might be some sort of function that has two inputs that tells you what the function's going to be. It doesn't even have to be two, it can be more than one. It's traditionally something like u and, it involves both an x and a y, traditionally, or z, but u is good because it's often like a utility or something like that. But it can be profit, it can be anything, and each of these will make that change, and if you put them in together it will make that something else. And what we want to know is if you change both the x and the y, how does the u change? And how quickly does it change? Which is the idea of how derivatives usually work. It's just we've got two things changing simultaneously. So and most of the time, how quickly u changes will be different depending on which x and y we're currently at. I don't really know how to say that, but it'll be a different formula depending on how you're at. So it's easiest to do this with an example, but I just wanted to have an idea of that. That's the basic idea. Okay. So one way of imagining a function like this is to imagine it as having an x and a y, and then every x and y produces an answer for u. So just if we did an example and the u was equal to 3x minus y times x or something like that, then at every possible x and y I could figure out what u worked out to be. So if I was here at 1, 1, then the answer would be 3 times 1 minus 1 times 1, which is 2. And if I was here at 2, 1, it would be 3 times 2 minus 1 times 2. 3 times. So x equals 1, y equals 1. U came out to 3 times 1 minus 1 times 1, which was 2. When x equals 2 and y equals 1, u came out to 3 times 2 minus 1 times 2, which is, interestingly, also 2. I did not mean that to happen. And if I had x equals 1, y equals 2, you would get u equals 3 times 1 minus 1 times 2, which would be 1. And basically every dot here, and they don't even have to be the whole number ones, every dot produces a different answer for u. So if I have 2 and 2, I'll get 6 minus 4, which is 2. And if I have 2, 3 and 1, I'll get 3 times 3 minus 3 times 1, which is 9. I'll get 6. No, 3 times 1, damn it. No, yeah. 3 times 3 minus 3 times 1, which is 6. I really feel like this should be a 4. Yes, that's a 4, not a 2. Sorry about that. Okay, the world makes sense again. Okay, and every dot produces a number. And so I can think of it as temperature if I wanted. It's hotter in some places than others. That's one way of thinking of it. And what most people think of it as is a height. That this one I interpret it as 1 above the page. This 1 I interpret it as 1 above the page. This 2 I interpret it as 2 above the page. This 4 is 4 above the page. This 6 is 6 above the page. And every dot produces a height. And then I can imagine some sort of thing that's sort of going up like that as it gets further away from the edge. That's how most people imagine these things. And they use that geometry idea to understand what's happening. Okay, cool. But in general, even without the geometry, I'm imagining if I'm at a particular spot, how do these numbers change? So say I just need to do a few more of them. 3 times 2 times 3, let's do 6. Oh, interesting. So if I was here, for example, around there, and I went this way, what would happen to the numbers? And I go, well, they tend to be going down this way and up that way, so I don't know, maybe it's going to be roughly constant, maybe it's going to go up or down, I don't know. And that's what I want to try and figure out. Okay. Doing well. So you've given me a chance because I don't get to prepare for these things, so I have to make it up as I go along. So what I would want to figure out was how quickly this changed if I went that way and if I went that way, and combine them together to produce how quickly it would change if I went in whichever direction I wanted. And so what we can do is this, that du on dx is how fast it changes when I change x without changing y. And this is how fast u changes when I change y but not x. And if I change them both simultaneously, then the amount of change that u has will be a combination of those two things. Okay. Did you do in this course a thing called the total derivative? No? Okay, it's all right, just checking. Okay. So essentially what I'm going to do is I'm going to pretend, in this one I'm going to pretend that the y is a constant and isn't really a variable, and I'm going to do derivatives pretending that the y is a constant, and this one I'm going to do derivatives pretending that the x is a constant. And so the way it works, this is one example, and then I'll just run into doing lots of examples. So I'm going to run through this and do derivatives the way I always do derivatives, except I'm going to treat anything that is not an x as a constant. So this is constant times x, so the derivative would just be 3. And then this minus, there will still be a minus there. This is also constant times x. So if that y had been a 7 and it had been 7x, then the derivative would have been just 7. And so I'm going to get that. So in my head, that's the thinking that I do. And I normally pick 7 because it's a nice number that doesn't have anything to divide into it, so it doesn't disappear when I do calculations. I pick a number to be y and say, well, what would I do if this was a number? What would I get? And I would get whatever number is there. And so that's what I put here. But on the other hand, du on dy, this doesn't involve any y's, it counts as a constant as a whole, and so the derivative of a constant with no y's in it at all is 0. And this, well, this would be y times number, which would be the same as number times y. And if I differentiate a number times y, I would get the number. Now, I can show you something that I do to make it easier for me to do that in my head. It's actually this. Anytime there's a constant multiplied on, it will still be multiplied on in the answer. That's how derivatives always work. So if I have 6 times all this stuff and I differentiate, it'll still be 6 times something. That's always true for all derivatives. So I can look at this and say, that x is a constant multiplied on, so it will still be there. And the derivative of just y is 1. I find that a much easier way of dealing with this. And so that's partial derivatives. So why don't I do some partial derivatives with these logs and exponentials to see if we can keep track of what's going on here. All right. Something like that. Okay. So, du and dx. Before I started, I'm going to have a look to see where the constants are and where the x's are. That counts as a variable because the x is the thing I'm differentiating as. That counts as a variable. That counts as a constant. And e, well, e is e. So, if this was x equals e to the 7x, I have 2 pieces that both involve x that are multiplied together, so I'm going to have to use the product rule to do it. So I'll differentiate the x, and that will give me a 1, and I'll keep the e to the yx, and then I'll keep the x, and I'll differentiate the e to the yx. Well, the derivative of e to the yx is just the same. The derivative of e to the anything is just the same. But then because of the chain rule, I'm going to need to multiply by the derivative of that. So the derivative of yx, well, the y is a constant and it's multiplied on, so it will still be there, and the derivative of just x is 1. So that's what this one turned out to be. Let's try the other one. Okay. So let's have a look at this. That's a constant this time, and that x there is a constant this time. So when I differentiate this, that x is a constant multiplied on, so it will still be multiplied on afterwards, because that's how derivatives work. If you have a constant multiplied, it's still there after you do the derivative. And then the derivative of e to the anything is the same as it was before. But then because of the chain rule, the derivative of this thing up here has to come out. And let's see, the derivative of this with respect to y, the x is a constant multiplied on, and the derivative of y is 1. So 1 times x. How do you feel about what happened there? Yep. So you'll notice that most of my differentiating tends to hinge upon me repeating mantras to myself. So constant multiplied on will still be there afterwards. Okay, so I'll deal with that. And then e to the power of is the same. Okay, I'll deal with that. And then the chain rule is this, so I'll deal with that. If I just keep saying these things to myself, it helps me do it. Difficult in exams because I'm not allowed to say them aloud, so I have to pretend that I'm saying them aloud. Damn it. Wait till I've figured it out. Let's do that one. We use ln in this course, that's how you write it, as ln? Okay. Some courses write log for that, so I just was checking. Okay. So let's have a look. This ln is a function, and inside it we have this stuff. So I know that if I have something inside a function, I'll have to use the chain rule. So let's see. So regardless of what's in there, I'm going to have to do this. So the derivative of ln of just thing should be 1 over that thing. That's how ln works. And the thing that I have there is x minus xy squared. But because of the chain rule, I will have to multiply by the derivative of this thing. Okay, so the derivative of x is 1, and the y squared is a constant multiplied on, so it will still be there, and the derivative of x is 1. So when I have 1 over times number, then this can end up on the top of the fraction. Oh, that's so cool, something's going to cancel out. That's cool. Oh, I can't help it. If I notice that I can factorize things, I tend to. This is not necessary, this bit, but I notice that I've got an x in both parts on the bottom. And so I can pull it out to leave me with 1 minus y squared. And then the 1 minus y squareds will cancel, and I'll just get 1 over x. I did not expect that to happen. That's cool. Okay. So let's try the du on dy this time. So I know that the derivative of ln of anything is always 1 over that thing. And the thing I had was 1 minus xy squared. And then I have to differentiate this. So the derivative of x is 0. The x is a constant multiplied on, so it will still be there. And the derivative of y squared is 2y. So I know the derivative of x is 0 because it counts as a constant for this derivative because they're doing a dy here. So it's traditional to put numbers at the front. So I knew that. I could cancel that one out too. There's an x here, and I can divide the top by x and the bottom by x and leave me with this. Huh. Cool. Okay. So that's doing partial derivatives. I'm sure there are many other places and things that we could make up to make this happen. How are people feeling about what happened there? Cool, good. So, it's at this point that it would be useful to know how to do second partial derivatives, because you asked about that. Just a second. Just for future reference, I'm going to call these. In case someone in a future semester comes and looks at these notes without watching the video, they know what we're on about. Okay, so there are partial second derivatives as well, second order partial derivatives. And that would mean continuing to differentiate after we'd already done the first couple. So the second order ones, you would have something like du on dx, and then you would differentiate it again like that, and that would produce the notation is that usually. And we could have du on dx and differentiate again, but this time do dy. And we could have du on dy and this time do dx. And we could start with du on dy and this time do dy again. So they're the traditional ways of writing these things. This is the action that we're performing. We're going to go u, I'm going to do d on dx and then d on dx again, and that produces this. But your lecturer also uses this notation. U is a function of x and y, and he called this fxx and fxy and fyx and fyy. So the reason why they're in different order is that the thing that is closest to the function that's being differentiated is the one that happened first. So the x is closest to the f, so it happened first. But this yx is closest to the u, so it happened first. That's why they're in an opposite order. No one really cares because it always works out that this answer is the same as this is the same as this, and this is the same as this, so it doesn't really matter. Well, I say always. There's some technical nitty-gritty that says that from very crazy and stupid and awful functions, sometimes they don't work out to be equal, but pretty much every function that actually you would think of to represent anything in the world usually doesn't do that. But I know that sometimes the people in physics have some weird-ass crap that doesn't work for. So, but economics is less weird than that in terms of functions. It's weird in other ways. So it's worth pointing out that these two will be the same answer. So these are the 4 second-order partial derivatives, and in my head I organise them like this. I do du on dx, and that gives me du on dx. I do d on dy, and that gives me du on dy. And then I might do x again. Or I might do y from this point. And this one I might do y again. And this one I could do x, and it will come to the same place as this does. And technically there's another layer of third-order ones further down if you really wanted to, but no one really cares about them. Okay, so here's the thing. Why do we even care about these second-order ones? Because the first-order ones told us how u changed when x and y changed. So that's what these ones here did. I feel like putting some circles around things so I can see where they are. That's easier to see. These ones tell you how u changes when x and y change. Well, this tells you how that changes when x and y changes, when x changes. This tells you how that changes when y changes. It tells you how that changes when x changes. And this tells you how that changes when y changes. So the second order partial derivatives tell you how quickly the first partial derivatives are changing. Right? So, and we're interested in those things a lot of the time. We say, oh sure, it's increasing, but is it increasing quicker as x moves? Or is it increasing slower as x moves? Because if it's increasing slower, then maybe it'll level off at some point. Okay, so these partial derivatives allow us to tell what is going on at a place where the first derivatives are 0. So before I get to that, I just want to talk about calculating them. let's go back to one of those. Let me do a new one. Yep, let's do that. It's going to be awful. Yeah, this is going to be worlds of pain. Maybe I shouldn't have done that. I'm committed. So du on dx, this involves an x, and this involves an x, so I'm going to have to do the product rule. So I will differentiate this, so e to the anything stays the same, and then because of the chain rule I'll have to do the derivative of this, and y is a constant multiplied on, and the derivative of x is 1, okay? And then I will keep the ln x plus y, and then in the second part I will keep the e to the x, y, and I will differentiate the ln x plus y, and the derivative of ln is always 1 over, and then I'll have to multiply by the derivative of this. The y will go to 0, the derivative of x is 1. Okay. It's not really that much simpler. I just decided that maybe I should bring the e to the power of x, y out the front of everything because it's in both parts. Okay, so if I wanted to do d squared u on dx squared, I would have to differentiate with respect to x again. I would take whatever answer I had for du on dx and I would differentiate it again. Oh, here we go. So this bit and this bit both involve x's, so I'm going to have to use the product rule. So I'll differentiate this bit. Now e to the anything stays the same, but because of the chain rule I have to multiply by the derivative of this, and the derivative of this is y, and then I keep this bit. And then in the second one, I'll keep the first bit and differentiate the second bit. Okay, so the derivative of this, well, y is a constant multiplied on, so it will still be there. And the derivative of ln of x plus y, we already know what that is. We figured that one out earlier. Okay, so I didn't have to use the product rule here because the y was a constant. And then the derivative of this, I guess you could use the quotient rule if you really wanted, but you could also rewrite it as x plus y to the minus 1. I could rewrite this like this, right? Oh no, I've used it now. Just let me give myself some space. Y ln x plus y plus x plus y to the power of negative 1. Yep. Okay. So when I have a power, the power will come down and it'll be x plus y to the negative 2, and then I'll have to multiply by the derivative of this, which is 1. Great. So I wrote it as x plus y to the power of negative 1 because that's what 1 over is. Ignoring the inside, the negative 1 power will come down, and then the power will go down to negative 2 because that's how derivatives of powers work. And then because of the chain rule, I had to multiply by the derivative of this, which produces that answer there. And that doesn't look like it's going to be all that fun to simplify, so I'm just going to leave it. Oh, you know what? Oh, nah. It's just painful. No, I can't leave it. I'm sorry. So this bit here, this y I've pulled in and multiplied the y by both of those. That's produced this answer. and y times 1 over x plus y is y on x plus y. And then this would be 1 over x plus y squared. It's not necessary to simplify, it just makes me feel better. And so they've both got an e to the xy in them, so I might pull that out. And we've got y over x plus y. Oh, and there's a second one. Well, that was painful. I will do another example that's less complicated in a second. So I just wanted to keep track of what I was doing. One thing that can be difficult is switching from the y to the x halfway, but I don't want to do it with this one because it's already too complicated. I got a bit ambitious there. So I would not expect your lecturer to have something this bad in the exam. You've only got a certain amount of time. Is your exam 2 or 3 hours? Sorry? 2? Okay. I would not expect them to, there's just not time. Let's do that one. This one's going to be a little easier to cope with. So du on dx. The y is a constant multiplied on, so it's still there afterwards, and the derivative of x squared is 2x. The derivative of e to the anything is the same, but then because of the chain rule I have to multiply by what's here. Oh, can I put a number there? I'm going to put a 3 there, because it feels nice. The derivative of this, okay, so the 3 is a constant, so it'll still be there when I differentiate that. And the y is a constant, it'll still be there, and the derivative of the x is 1. Okay. Let me do the other straight up direct derivative, the first derivative. Let's do it with y. X squared counts as a constant, and it's multiplied on, so it will still be there. And the y, derivative of y is 1. The derivative of e to the anything is the same as it was before, except I have to times by the derivative of that because of the chain rule. So the 3 is a constant still there, x still there. Right. So now let me start doing the second partial derivatives. So this is, it's got 2 dx's. So I started with du on dx, and then I differentiated it again with respect to x. That's what that is. So I take the answer for du on dx, which is here. Just going to underline it with my texter so that I can see where it is. So the derivative of this with respect to x, the 2 will still be there because it's multiplied on, the y will still be there because it's multiplied on, and the derivative of x is 1. And then this, the 3y counts as a constant, so it will still be there. And the derivative of e to the 3xy, we already did that when we did the derivative earlier. So I get 2y minus 9y squared e to the 3xy. Okay. Let's do this one. d squared u on dy squared. So that's the same as d on dy of du on dy. So I'll go back to find du on dy, which is there, and I'll differentiate that. Can I fit it all on the screen at once with my great big writing? Okay. So x squared doesn't involve any y, so that's going to go away. That's going to disappear entirely. The 3x is a constant when I'm doing y, so that will still be there. And then when I differentiate e to the anything, it's the same. But then because of the chain rule, I'll have to multiply by the derivative of this, which is 3x, because we did that already. So that's minus 9x squared. Okay. which leaves only one more derivative to do, which is the dx dy. Because we don't need to do the dy dx and the dx dy, they should be the same answer. So according to the way I've written it, it should be that. So I could do du on dy first and then d on dx, or I could do du on dx and then d on dy. It doesn't really matter, but this is the order I've written it in. So if I go back to where d on dy was, du on dy, that's there. Just underline that. So I'm doing it d on dx now. So I'm taking this one and doing d on dx. So the x counts as the variable and the y counts as the constant. So x is a variable, that will become 2x. And this one, they've both got an x in them, so I had to use the product rule. So the derivative of 3x is 3, and I keep the e to the 3xy. And then I keep the 3x, and then I differentiate the e to the 3xy with respect to x. So I'm doing x, aren't I? So the y counts as a constant. Okay. This is the hardest one to not make a mistake, because if you've just done y and then you do x, everything, yeah. Here? Yep. So this is not 3xe. Here? Well, this was me saying I need to differentiate that there and keep it there, and keep that here and differentiate it there. I did the product rule. Is that all right? Yeah. And so I get 2x minus 3 e to the 3xy minus 9xy e to the 3xy. I just pulled this minus into both of them at the same time. So yes, this came from the product rule. Is that okay? Cool. Sometimes I've just done it wrong, so it's good for you to ask me. And so that's all three, technically four. That's all of the second partial derivatives of this thing, which all look like that. And if you really want to have time and you really want to check if you're doing everything correctly, this one I went to the dy and I differentiated dx. If I went back to the dx and differentiated at dy, I should get the same answer. And I'm just going to check the first one. If I differentiate this with respect to y, the 2x is a constant. Yep, and so the beginning is correct. It's working out the way I want. I don't want to do the rest. That's too much. Okay. So that's how to do second partial derivatives. And then the question is, what are we going to use them for? And what we're going to use them for is finding out what the maximums and minimums of a particular function are. And if it's not a maximum and a minimum, is it a saddle point? Okay. So when we imagine that function, there are many things that could happen, which is why I kicked myself for not leaving the Play-Doh here yesterday. Oh, actually, just a second. It's too clear. No. So functions can do that sort of thing and have a maximum. They can do that sort of thing and have a minimum at the bottom. And sometimes they can go up in one direction and down in the other. Paper doesn't do it very well. So some things have a maximum like that, top of a hill. Some things have a minimum like that. And some things are a maximum in one direction and a minimum in the other. And a good place to see it is in this. That's a minimum this way, but it's a maximum that way. So the place where your thumb is there, if you hold it upwards, maximum if I go this way, minimum if I go that way. That's a saddle point, right there. Pringles used to be that shape, but they're not that shape anymore. It's very sad. And it's the shape of the saddle of a horse, in particular of a camel actually. If you're sitting on a camel where the hump is, a two-humped camel. If you're sitting here, then if you go that way it's a minimum, and if you go that way it's a maximum. So if you put a saddle on your camel at this spot, then that would be the middle of the saddle. That's why it's called a saddle point. There you go. Whereas up here at the top of the hill, that's the top. No matter which direction you come at it from, it's the top of the hump. And so that's a proper maximum. And your camel doesn't have any minimums on its back. Okay. So okay. So if we have a function which describes how high something is, and maybe it describes the profit or the utility, we would like to know where is the maximum, if there is one, where is the minimum, if there is one, and are there any saddle points where if I come past it in different directions, I have a different experience of what's going on. I want to know those things. And the cool thing about a maximum is that no matter which direction you approach it from, when you get to the top of that hill, then just for a moment you stop going up and start going down, and so the derivative is 0 at the top. No matter which direction you're going, it will stop increasing and start decreasing, and for a moment the speed at which it changes will be 0. Because it will be not going up and it won't be going down as it switches over, no matter which direction you come at it from. In particular, if you just change the x and just change the y, it'll be 0 when you do the derivatives in both of those directions. At the bottom of a minimum, the thing will happen at the same time. And saddle points do that too. If you come from one direction, it's a maximum and the derivative is 0. If you come from another direction, it's a minimum, the derivative is 0. So these points happen when the first derivatives are both 0 at the same time. And so to find them, a maximum or a minimum or a saddle, we need both or all, however many there are, first derivatives to be 0. That is, we need both du on dx equals 0, and at the same time du on dy has to be 0 simultaneously. It is possible sometimes to get du on dx to be 0 but not have du on dy being 0 at the same time. Rare, but possible. And it is possible for the other one to be 0, but if they're 0 at the same time, that's when you get a maximum or a saddle point. Oh, there's a saddle here just in my knuckles as well. Up top there, bottom there. So you have one in your own hand, and they can't not let you take a hand into your exam. So, okay. But that's why you need them. And what that will guarantee is if both those derivatives are 0, then the rate of change in every direction simultaneously will be 0, and it's definitely going to be a maximum or a minimum, or possibly a saddle. Now, it's going to be hard to tell without drawing the picture, and you don't have a 3D graphing software with you, to tell which of them it's going to be, and that's why we need the second derivatives. These second derivatives that we calculated here are designed to help us, well not designed, they happen to help us tell whether it's a maximum or a minimum or a saddle point. So let me do one. I believe they call these stationary points. If you look online, some places will call them critical points. But they're stationary because you stop going up and start going down. For a moment, you're still. Okay, so find stationary let's do it with an F instead of a U this time. Oh no, I don't like doing this off the top of my head. It's bad to just make them up because I won't know if there's going to be one. So just let me Google one. Ooh. Just trying to find a good example. All right, well, let's see what happens. It looks complicated, but bear with me. Okay, so if I want to find stationary points for this, I'm going to have to find its partial derivatives. So fx will be, all right, so this involves an x and this involves an x, so I'm going to have to use the product rule. So the derivative of this would be, well, the y minus 1 is a constant multiplied on, so it will still be there. And then I'll keep this bit. And then I'll keep this first bit. And then I'll derivative this bit, which will be the same because that's how exponentials work. But then because of the chain rule, I have to multiply by the derivative of that, which is minus 2x, because the y will disappear when I'm differentiating with respect to x. So y minus 1. So just a second, let's see if I can make that a bit simpler for myself. E to the minus x squared minus y squared is in both of them. I've got a y minus 1 here. Actually, there's a y minus 1 in both of them as well. That's cool. And then I've left behind a 1 there and a minus 2x squared there. Okay, that's what fx is. I'm just going to do some underlining to make sure I've got that right. This was in both of them, and that's here. And then this was in both of them, and that's here. And the bit left behind is just a 1 because I've removed everything. And at x times minus 2x is minus 2x squared. Yes, I've done that right. Okay, and fy is, okay, product rule. The x is a constant, it will still be there. The derivative of y minus 1 is 1. So that's the derivative of that bit, and then I keep this bit. And then I keep the x, y minus 1, and I differentiate this other bit. Derivative of e is the same, and because of the chain rule, I have to times by the derivative of that. That's a constant, it goes away, minus 2y. So what have we got? There's an x here and an e to the thing here. There's an x here and e to the thing. So I've got x e to the minus x squared minus y squared. And I'm left with a 1 and a whatever this is. Y times minus 2y would be minus 2y squared. Okay. Cool. So they're my two partial derivatives. At the stationary point, both of them are 0 at the same time. Yep? Let's just see. The derivative of y is 1, and the derivative of minus 1 is 0. Yep. Okay, so for a stationary point, both fx is 0 and fy is 0 at the same time. So I'm going to need to make them both 0 and see what happens. So let's see. So f of x equals 0 means that y minus 1 e to the minus x squared minus y squared 1 minus 2x squared has to be 0. And the only way, well, let's see, these are three things multiplied together and are equal to 0, so for it to be 0, one of them has to be 0. So I get y minus 1 equals 0, or 1 minus 2x squared equals 0. And the reason I haven't included this one is that e to the anything is never 0. So either y equals 1, or 1 equals 2x squared, half equals x squared, and x squared is whatever this is. So I have to do the square root of this, and when you square root a fraction, you can square root the top and the bottom separately. Okay. So that's when fx is 0. At any of those places is when fx is 0. Fy is 0. What do we get? We got x e to the minus x squared minus y squared. So either x is going to be 0 or do not like it, Sam, I am. Quadratic formula, I guess. This is good. Good with that. Quadratic formula, that's a quadratic equation, and I can't think of a way of factorising it. So I'm just going to see what happens. Y equals minus b, that's this bit, plus or minus b squared, minus 4 times a times c over 2a. So that was me calling this A and B and C in the quadratic formula. Okay, good, good, good. I do these things to myself. 2 plus or minus the square root of 4 plus 8, so 12. There you go. That's not fun. I guess the 12, I could make it a bit simpler. I guess the 12 is a 3 times 4, so I could square root the 3 and the 4 separately. Because I can do the square root of the 4 and the square root of 3 because they're multiplied together. And now everything's got a 2, so I can divide everything by 2. Still not that good. So what have I found? I've found that fx is 0 when y is 1 and this one when one of these happens, and fy is 0 when one of these happens. So I'm just going to summarise that so that I know where what I'm doing. And I'm just going to separate the things with the different answers, 1 on root 2 and minus 1 on root 2, and fy is 0 when x equals 0, or just so I can start, I'm separating the plus or minuses so that I can see them. Okay, so I need something from here to be true and something from here to be true at the same time in order for both of these. So I have to combine them together or they're not both going to be 0 at the same time. So I could have y being 1 and x being, if y was 1, the x would have to be 0 in order to make it come out for them both to have something from each. So I could have y equals 1 and the x has to be 0. If y was 1, I can't have that because I've already chosen what y is. X could be 1 on root 2, in which case I've already chosen what the x is, so I could get 2 options for what y could be. Or the x could be minus 1 on root 2, and I get 2 options for what the y could be. I'm sorry they didn't come out to be nicer numbers. I just wanted to be very systematic about this. I chose the y equals 1, and that went here, and the only way I could do that is for this one to be 0 at the same time. And then I chose the x equals 1 on root 2, and there were 2 options for what the y could be if I chose that x, and then I chose the x to be minus 1 on root 2, and there were 2 options for what the y could be if I chose that one. Okay, so I've covered everything. So with this one, the x is 0, which makes the fy 0, and the y is 1, which makes the fx 0. This one, the x is 1 on root 2, which makes the fx 0, and the y is this thing, which makes the fy 0. Yep, it all works. Both of them are 0 at the same time at all of those 5 points. There we go. I have 5 stationary points for this function. Sometimes you only get 1, sometimes you get 5. Okay. Well, the next stage will be to try and figure out what kind of stationary points these were, which would require me to find second partial derivatives. And I don't know if I want to do that for this function, because they were pretty awful as it was. And do you know what? Those second partial derivatives aren't going to be too bad. Oh, actually they are. No, I'm going to do it. I'm going to do it. So let's see. fx was this. I really don't want to get these mixed up. fx was this. I'm just copying it from where it was. Was that. And so fxx, well, let's see. That's a constant multiplied on. And then this bit I'll have to use the product rule for. In fact, do you know what? I'm going to do the product rule having this piece and this piece. So when I differentiate this bit, that's a constant multiplied on. And then the derivative of this bit is minus 4x. And then I keep the e to the minus x squared minus y squared. And then I keep that first bit and I differentiate this bit and I get that. Okay. Well, everything's got a y minus 1 and an e to the minus x squared minus y squared, and then we get a minus 4x minus 2x. Yeah, rightio. Cool. I should have pulled out the x too. They've all got a minus x as well. Whatever. Let's do the fxy. Okay, so with the fxy, I differentiate. It's still a product rule that involves two y's. So I'll differentiate this with respect to y. So that 1 minus 2x squared is a constant multiplied on, so it will still be there, and the derivative of y minus 1 is 1. And I'll have this, and then I'll keep that, and then I'll have to have minus x squared minus y squared times the derivative of that, which is minus 2y. The more practice that we can have at seeing how derivatives are done, the better. So everything has a 1 minus 2x squared and an e to the minus x squared minus y squared, and what we're left with is a 1 and this thing, so a minus 2y squared and a plus 2y. Oh cool, we had that already, that's fun. And fy, if I copy it down from before, was x. And so the fyy will be the derivative of this. So I'll differentiate that. The x is a constant multiplied on. The derivative of this would be minus 4y plus 2. Keep this bit. Keep the 1 minus 2y squared plus 2y and differentiate this bit. So there's an x and an e to the minus x squared minus y squared in both of them. And we're left behind a minus 4y plus 2 minus 2y plus 4y squared minus 2, whoa, cubed. Wow. Sweet. Four y cubed minus 2y squared minus 6y plus 2. Okay, that's what it is. Cool. So if I want to do these at some of these points, how about I just do one of them? So at 0, 1, fxx comes out to zero, because I've got a y minus 1. 1 minus 1 times stuff, which is 0. And the fxy comes out to one minus 0, e to the whatever it is, minus 1, and 1 minus 2 plus 2. Whoops, sorry. Okay. And f of y comes out to 0 times stuff, which is 0. Okay, so according to the rules that are written in the notes, if you find a critical point and then you look at all of these second derivatives, you can create this calculation, which your lecturer doesn't seem to have given a name. I call it the discriminant. You can do this calculation, f of x, f of y minus f of xy squared. And so we have 0 times 0 minus e to the minus 1 squared which is a negative number, because e to the something is always positive. So if this calculation comes out to be negative, it's a saddle point. And that's the sort of decision we would have to make. You would have to sub in that point and see what the 0, 1 was. And then you would need to sub in one of the other points and figure out what that was as well. But I don't care to do that, because my points are awful. But I won't do it, I'll just get it started. At that point, you would go fxx equals, and you would sub it in and see what you get. No. There it is. No, that's xy. Sorry. Where's xx? fx, fy. That's finding the stationary points. There's the second derivatives. There it is. E to the minus something. And minus 6 times 1 on root 2 plus 4 times 1 on root 2 cubed. And so whatever that is, you would need to figure out what it was. And a calculator would help you to go, well, it's whatever this number is. And then you would have x, y, and f of x, y. And then you would go f of xx times f of yy minus f of xy squared. And it would come out to a number. And whatever number that came out to would tell you whether it was a maximum or a minimum or a saddle point. I know in advance, because I've seen the answer, that this one is that there's only one saddle point in this picture, and the other two, there's 2 maximums and 2 minimums. I don't know which one is which, but let's just pretend that this one comes out to be a maximum. Positive. No, that'll make it a minimum. No, it wouldn't. So all of the other 4, this comes out as positive, and then what you'd need to do is look to see whether this number here was positive or negative. So if this came out to a positive answer, then you know it's either a maximum or a minimum, but you have to decide which one it's going to be. You know that if it's negative, it's a saddle point, and if it's positive, it's one of a maximum or a minimum, but you have to decide which one is which, and you just look at either one of these two, and xx being positive means that it's the top of a hill. No, xx being positive means it's downwardly curving, upwardly curving, which means it's the bottom of a hill. So now we would need to look at fxx or fyy, it doesn't really matter. If fxx is positive, then that means it's upwardly curving, and so it's a minimum. If fxx is negative, then it's downwardly curving, which makes it a maximum. And that's how we decide. I wish I had had an example which had one that was a maximum or a minimum. Just let me have a look. All right, I'm going to do one more because I'm feeling comprehensive today. Okay, so fx this time is 2x, the y disappears, plus 3. Fy, 2y plus 2. And we need them both to be 0 at the same time for a stationary point. And so we get, no. Stationary point. You need 2x plus 3 to be 0, which means that 2x is minus 3, which means that x is minus 3 over 2. And we also need 2y plus 2 to be 0. So 2y is minus 2, so y is minus 1. Yep. And so both of those have to be true at the same time in order to have a stationary point. And so therefore the stationary point has to have these coordinates. So now I can do my second derivatives. f(x)(x) is 2. f of xy is, well, 0 because there's no y's in that at all. And f of yy is also 2. And so f of x, f of yy minus f of xy squared is 2 times 2 minus 0 squared, which is 4. And because that's positive, which means it's either a maximum or a minimum, and then we go and have a look at what f(x)(x) or fyy is. And so we have f(x)(x) is positive, which means it's upwardly curving, because that's what the second derivative does, is how does it curve upwards, and so therefore is a minimum. So there is a minimum at minus 3 on 2, negative 1. So this function has a minimum at minus 3 on 2, negative 1, and it doesn't have a maximum. And technically I don't really know if it has a local minimum here, and presumably it doesn't have any others, otherwise it would come back down past this. And the actual minimum is f of minus 3 on 2 minus 1 is minus 3 on 2 squared plus minus 1 squared plus 3 times minus 3 on 2 plus 2 times minus 1. Because I'm just subbing those things back into the formula. So 9 quarters minus 9 halves is minus 9 quarters, 1 minus 2 is minus 1, minus 1 minus 9 quarters be 4 quarters minus 9. Yay! So that's unconstrained maximization or minimization, whatever it is, unconstrained optimization. That other function that I had there has 2 maximums and 2 minimums, and whichever of them is higher is the actual maximum. So you've seen a lot of David making decisions about how to do derivatives today, and I'm hoping that covers these first few things as much as you could ever want. Okay. Any questions or thoughts about any of that before I move on to something else? Cool. Well, that covers sort of all of that. Did you have the specific example that you wanted to go through?
Year exam.
Yep.
I'm sure there's a couple on there. I didn't specifically pick
All right, let's go. So this is the last year exam your lecturer gave you.
Yeah.
Okay. How many past exams did the lecturer give you? Just this one? Okay. Sure. This is good to know, actually, just for future reference. Hey, when is your exam? Wednesday? Okay. Maths Learning Centre is open all the way to the end of exams, so we will be open next week as well. So if you want to come in next week, you can come and talk to us, but also this week. The big first year Maths and Engineering exam is on the Monday, so it should be pretty quiet on Tuesday. That's a last-ditch effort the day before your exam, of course. Okay. I'm not offended. It's fine. So the average... So you're thinking about these sorts of things. Ah, cool. When I said total derivative, in this course that's called the small increments formula. I just didn't know what it was called in this course. I thought it was going to be here. Okay. All right. I mean, I don't really know where to start. I mean, there's all sorts of things that I could talk about. Right, let's look at 4. So we have demand is 4p plus q minus 16 is 0, and total cost is 4 plus 2q minus 3q squared on 10 plus q cubed on 20. Of course it is. That's so realistic. Find total revenue, pi, marginal revenue, marginal cost in terms of Q. You don't have to write this if you don't want, but I have to because I have to give your thing back. Oh no, it'll just be easier when I scan this to have it on the page. And then I can draw on this. Find Q that. Maximizes profit. This Q MR equals MC. Okay. So there's a lot going on here in this question, and there's a lot to do. Because this one's really 1, 2, 3, 4 things. Okay. So my usual way of dealing with any problem is to ignore what the goal is to begin with and just have a think about what it means. So I have a total cost. So this says if I produce Q of these things, then this is how much it costs to produce all of them, the entire bundle of Q of them. That's the idea. That's what total cost means. Is it? As opposed to marginal cost, which is how much it takes to produce the extra one. Okay, cool. And then this demand is what will dictate the price I'm capable of selling these for. Is that the idea? Okay. So if I wanted to know the revenue, then presuming that I'm able to sell all Q of these objects, I could go Q times whatever I sell them for, and that would be the revenue. And then the profit would be the revenue minus the cost. Okay, cool. So I would need to figure out, so cool, just thinking it through. So presumably I can figure out the P from here based on the Q. And so I should be able to calculate the price times the quantity, which is the revenue. Okay, I've got a plan, I think, of what I could be doing in this question. Now let's ask what it actually asks me to do. Total revenue. Okay, I need to find the price, and then it will be price times that. Profit, I can do total revenue minus total cost. Marginal ones should be derivatives. Because marginal anything is a derivative. Because all of these assumptions are that the Q is actually in millions or thousands, so that, because a derivative only works for a very small change, and so you need the change to be small relative to the size of the object that you've got. So if your Q's in thousands, then 1 is 1,000th of what Q is, so it all works. Okay, and so then the derivative should be 0 at the maximum. All right, well, let's see what happens. So from the demand equation, I should be able to figure out what the price is. Like that. So I can subtract the Q and add the 16, and that would produce this, and then I should be able to divide by 4. And it's probably nicer to write it like this. Oh, that is not a Q, that's a theta. So taking this equation and using it to tell me what the price is a useful place to start, because then I know that total revenue equals quantity times the price you sell it for. And so that would be Q times 4 minus a quarter of Q, because that's what this is. Some people will write this as Q on 4, which is perfectly acceptable, but I think in coefficients, and so I like to put the quarter there. So I took the answer for what P is and I put it in there. Okay? It may or may not be necessary to expand that out, but I just decided I would anyway, just in case. Okay, so that's the total revenue. The profit, that's what this pi stands for, I imagine, per for profit. It's total revenue minus total cost. So the total revenue was 4Q minus a quarter of Q squared, and the total cost was this thing. I've just converted my original formula into things with coefficients because it's easier for me to think about that way. So I've got 4Q minus a quarter of Q squared minus 4 minus 2Q plus 3/10 of Q squared plus minus. Oh, I don't want to add a quarter and 3/10. Maybe I should do it in decimals. 3/10 is 0.3 and a quarter is 0.25, so 0.55. That's not too bad. Oh, it's taking a quarter. Oh, it's 0.05. Oh, that's cool. Oh, sorry. No, I'm just trying to do this because they have a common Q squared. So that's 0.3 minus 0.25, which is 0.05. So 4Q minus 2Q is 2Q. Combining these two together would be a 20th of Q squared. Okay. I'm just going to do a little bit just in the side. 3/10 minus 1/4. Just want to make sure I've done my working correctly. So that would be 6/20 minus 5/20. Yay! It does work. Okay. Okay. I think I've done all that right. These two. Yeah, that's everything that matches, and that's definitely a minus. And that one is a plus. Yeah. Okay. Okay, so that's pi. And then what else did they ask me to find? Marginal revenue. So marginal revenue would be the derivative of total revenue. So I need to go back and find my total revenue formula. Oh no, it's actually just here. I've got that. 4q minus a quarter of q squared. So the derivative of that with respect to q is 4. The quarter will still be there, and then q squared would become a 2q. And a quarter times 2 is a half. All right. And the marginal cost. So that would mean going all the way back to my original cost function. That was this thing here. The derivative of the 4 is 0. The derivative of the 2q is 2. The derivative of this would be 3/10 having to times by 2q. And this would be 1/20 times 3q squared, because that's how you differentiate q cubed. Okay, squared. 3/10 times 2, because the 2 would cancel with one of the 2's, the 2 that's part of the 10 to give a 5. Yep, okay. So I have all of the answers that they asked me for now. If I had time, but I wouldn't in an exam, but if I had time, I would summarise it at the bottom and say this is what they all are, so that the person reading it didn't have to work too hard to find them. Okay. And then the next question is, I've lost a page. No, I haven't. Okay. Then the next question is solve d pi on dq equals 0. Okay. So d pi on dq is 2 plus 1/20 times 2q. The 4 will disappear, minus 1/20 times 2, 3q squared. And we want to make that equal to 0. Ugh. It's got all those fractions in it. So why don't I multiply everything by 20, and then all the fractions will go away. And it's traditional to have a positive coefficient on your q squared, so I'm going to switch all the signs. So I've done minus 40 and minus 2q and minus 3 squared, which is giving me a plus 3 squared, and technically minus 0, which is giving me a plus 0. Because minus 0 is the same as just 0. So I need to solve this. So I could there's two options. I could attempt to just factorise it straight up. If I could imagine things that no, can't be bothered because of this 3 here. That's annoying. So I'm going to use the quadratic formula. So minus b plus or minus b squared minus 4 times a times c over 2a. So what have we got? 12 times 40, which would be 480. That's awful. No, this can't be right. I can't square root 484. This is when I get a calculator and I figure out what square root of 484 is. I guess 4 goes into it, and that'll leave me with 121. Oh wow, look at that. Okay. Of course, it never happens that way, so usually decimals. So that's 121 times 4, and the square root of 4 is 2, and the square root of 121 is 11. I know my squares. And I'll divide everything by 2, and I get that. So one of those is negative, which doesn't make any sense. So that one doesn't make any sense because it's negative, and this Q is supposed to be a number of quantity of objects, and so it must be that one. So Q must be 12 over 3, which is 4. Right, we did it. I'm just going to put a comment here. This one's negative. So, not valid. Okay. Cool. And what was the last bit? Verify that at this Q, MR equals MC. Okay. So at Q equals 4, marginal revenue, which is still over here, is 4 minus a half times 4, which is 4 minus 2, which is 2. And MC is 2 minus 3/5 times 4 plus 3/20 times 4 squared. 2 minus 12/5. Well, there's a 4 in the 20. That's 4 times 5. Oh, yay. And that's 12/5, and so we get 2. Sweet. So I've just done some tricks there to avoid having to figure out what the answer actually is. See, this has got a 4 in it, and that's got a 4 in it, and so they'll cancel each other out to leave me with a... Technically, it's this, right? Yeah. So I could show that by going cancel 5, cancel 4 if I wanted. Okay, and so yes, marginal revenue is marginal cost. That's the conclusion. The word verify means check that it's true. So sub it in and see what happens. Okay, cool. As you can see, I always need extra paper in an exam, when I do one personally, because I write huge. But it's probably just from years of having to do lectures and write big enough so that everyone at the back can still see. Okay. Does anyone else have one in here that they've seen that they're not sure on what to do? Did you ask something before? No, that was partial derivative stuff, wasn't it? Okay, right. Okay. Well, I want to know this because I don't know what any of these terminologies mean, so I want you to tell me. So question 8 from the same exam. This says this. Q is 1000 minus 5p minus pa squared plus 0.05 y cubed. Okay? Where p is 15, PA is 20, and Y is 100. So this says, find the price cross price income and then estimate percentage change in demand if PA rises by 2% is the alternative good substitutable or complementary? Okay, there are a lot of terminologies in this question, and I currently don't know what any of them mean. So I'm going to have to get you to help me. I'm presuming that at least one of these has a derivative in it. So, okay, so first let me have a handle on what this is. So the demand normally indicates the connection between the quantity and price for the people who are buying my product. Yeah? Okay, and and presumably this P is the price. What is this Y? Income. And what is this PA? The price of this alternative good. Okay, that's good. Doing well. Okay, so as long as I know what all of these things are. Okay, so at the moment my good is 15 and the price of the alternative good is 20, so I'm selling cheaper. Okay. Okay. So the price elasticity of demand, I'm presuming, has something to do with dQ on dP, but I don't know. Can you tell me what it is? Can someone tell me what it is? That? Is there a symbol for price elasticity? No? Sorry? It just makes me feel better to have it, something equals this. Okay. Oh, so that's actually the percentage change in Q relative to the percentage change in P. So just making sure that I've got this right. This is the same as that. If dQ is a thing. So the change in Q relative to Q, that's the percentage change in Q. Okay. Okay, I just sometimes need ways of connecting bits of information together. So totally this formula would need to go on my cheat sheet because I don't know what it is already. Okay. Price elasticity of demand is that. So I'm going to need to figure out what dQ on dP is. I know the value of P at this moment. I know the value of Q at this moment. So if I can figure out what dQ on dP is, then I'll get what I want. Are we assuming, therefore, that all of these things are constant? So it's technically that with a partial derivative? Okay. So the 1,000... Right. The 1,000 will go away. That'll be a minus 5 from the 5p. That'll go away, it's just minus 5. Cool. That was easy. Hope that doesn't stuff my photocopier later. Okay. So, and we also knew that the p was 15 and the q was, well, we need to know what the q is. So we know that P is 15 and the Q is 1,000 minus 5 times P minus 20 squared plus 0.005 times 100 cubed. Wow. And why shouldn't it be? $50, $75. Well, times 100 would put it there. Times another 100 would put it there. So 50, 100. Okay, I think 100, 100. Yep. So 6,000 minus 400 would be 600. Right. But that's what calculators are for. I just like to practice my mental arithmetic, because if I don't, it sort of fades away. Okay, and so therefore the E is 15 divided by 5525 times minus 5. And that one I do not plan to do without a machine. I guess they've all got a 5 in them, but no. 15 times minus 5 divided by... Four decimal places. Sure. Okay. Tell me about this cross-price elasticity of demand. It's got to be something to do with both P and PA. Is it like P on PA times D? No. Oh, right. So it's the price elasticity of the other price, of the other price. Yeah. So this is like the alternative EA. Cool. Good-o. So that 0, that 0, that 0 will have a minus 2 PA, according to that. So at this point, the PA was equal to 20, so that's minus 40. And the Q is still the same. We know what Q was. That was 5525. And the PA at this point was 20. And so the elasticity is 20 over 5525 times minus 40, which is quite a bit bigger. I don't know how many decimal places he wants, so I'm just going to give you 4. Okay. So the income elasticity of demand is the same, but with Y in the position of P. Yay! Yep, good. Oh, sensing it. I could do that all by myself. So dq and dy, let's see, 0, 0, 0, the 0.005 will still be there, times by 3y squared. To 50, no, 150. Right. So income is usually positive, like the opposite direction to the way the price goes. I'm just checking that my that the numbers are coming out reasonable. So the EY is the 100 divided by the 5525, which we already figured out, times the 150, which is going to be an even bigger number than last time. Okay. All right, estimate the percentage change in demand, so demand being the Q, if PA rises by 2%. So, just a second, that's what elasticity is, right? It's a percentage change relative to a percentage change. So I can just use the elasticity directly to find that. So this is approximately the change in Q over Q divided by the change in PA over PA. That's approximately what it is. So this is a percentage change, and that's a percentage change. So basically, so that's saying, I know it's not called D on the original thing, but I decide it's called D. So this is saying that the elasticity alternative is like the percentage change in Q over the percentage change, well, approximately in PA. That's what it is. And so, therefore, the percentage change in Q would have to be EA times, well, approximately the percentage change in PA, which would be, in this case, we figured out what that was. That was minus 0.1448 times a 2% rise. Do I have to do it as a decimal, or can I just do it as a number? Does anyone care? Or it doesn't matter. Okay. So if PA rises by 2%, Q falls by 0.2. Approximately, just rounding it off. So here's a question. What does the phrase substitutable mean? I'm hoping that it's based on this answer here. So, what does substitutable mean?
You don't substitute, but it's if the price of good one drops, you substitute it for good two. Oh, sorry, it rises, you substitute it for good two because it's cheaper.
Okay.
An apple and a pear or something.
Does this help me make this decision, or what? Sorry?
Yeah, it should.
All right, well, it's a complementary good because we already figured that out. So we didn't need this answer to find it. We could just get it directly from this number here. Okay. So they're complementary goods, apparently. Okay. Yay! Okay, so my first piece of advice for cheat sheets is that you need the meanings of all of those words and how to decide things on it. Well, I would anyway, because I've only just learned these words. But you would have only just learned them in the last, 3 months, and so that's, yeah. So if I was going to have advice for cheat sheets, you need things on your cheat sheet to tell you really formulas, obviously, but what to do and how to decide. And it's especially important for terminology. So if there are terminologies, if you need to know what those terminologies mean in order to answer the question, then you need to write down what they mean. If it says elasticity and there's a formula for that, that needs to be there. And also things like, well, how is elasticity related to the question of percentage changes in one thing and other thing? I was able to figure that out on the fly, knowing a few of them and making a good guess. So I think I'd do quite well in the exam if I had a cheat sheet. My problem would be not being fast enough. I'm quite slow. Of course, I'm faster when I don't have to explain my thinking aloud to people watching me. So that would be better. I think the other thing about cheat sheets is that if you're going to practice using a cheat sheet, then you need to really, really make sure you take it with you. But also, you need to know where things, you should practice doing it in an exam sort of situation with it. So the worst, humans will do whatever it is that they practiced. So the classic example is that when you learn first aid, they used to teach you how to use an EpiPen by practicing it on yourself because it became quite painful. But what would happen is that in real life, when someone wanted to use an EpiPen, they would get it out of the person's bag and ram it into their own leg because that's what they practiced. Because when you're in a stressful situation, you do whatever it is that you did when you practiced. So therefore, you should practice using your cheat sheet in exam conditions. So when you're using your cheat sheet, don't practice using it also in the presence of all of your notes and the chance of asking people what to do. And every time and the other thing I would say is every time you try and do a question and you have to try and remember something in order to do it, that thing has to go on the cheat sheet. So that's what I would recommend. If you go through a past exam or even a tutorial or something and do it without your notes present, try that and go, right, underline all the things you're going to need to remember. All of that has to go on the cheat sheet because then you're going to need it. And it seems obvious when you say it that way, but sometimes you don't think about it when you're doing it. And the final thing is, it's never a bad plan to just sit down every so often and try and remember all the things without the cheat sheet, just in case you forget. And you don't want to be in that situation, but you wouldn't want to completely tank just because you couldn't have it. So can I check in this course, are you allowed to have whatever you want on there? Like, is it allowed to be typed? Yeah. Cool. Some courses it has to be handwritten, so it's just you need to check the rules. Are you allowed both sides? Yeah. Good, because they usually, if you have one, they have it double-sided because no one wants to check. So it's just easier for them. Just check those rules. And yeah, you need to know what's where on there so that you're not looking for things. So some people like to put worked examples on there. I find that really unhelpful when I had a cheat sheet in an exam because then I had to read the example to find the information I needed. So if you do have examples, then highlight a piece of it that's really relevant. But I wouldn't put examples on there unless I had a whole page to fill and then I just might help. So yeah. But mostly terminology is the most important thing. And decision-making processes and formulas. That's pretty much everything. That would be my advice for that. Cool. Well, thank you. Drop-in centres open all the way to the end of the exams. Feel free to drop in. Know that it will get busier as the exams get closer, but we will have more staff as well. And I personally will be there tomorrow and not on Monday, but there's plenty of staff there who know about these things, and give them some grace. And if they ask you what a terminology is, then it's a good idea that you have to put it on your cheat sheet.